Computer here recording, and we are recording. Very cool. We've got a homework, and it's due tonight, midnight, and that is homework 9. We also have another homework released. That is homework 10, and it is due next week. And then we're going to do review for our final, and we'll have 2 weeks to do the final, and that'll be take home with Blackboard and 2 stabs at it, and that'll give you an opportunity to effectively look at the homework on your own, do it offline, and then submit it, keystroking it in. So that'll give you enough time, I think, to look at the homework, and we'll have enough time to do some nice review for it. One of the questions that we have here on homework number 9 involves the twisted ring counter. That's a twisted ring counter in there. What I'll do here is I'll rewrite it so that you guys can see it. So it's basically JK flip-flops. And the tricky bit, you can see J sub B is wired to A, J sub C is wired to B, J sub D is wired to C. But D goes back to K. And the D prime goes back to JA. And this is a twisted ring flip-flop. And it relates to one of the homework questions. I forget which one. Let's go back and take a look. It's homework 9, and I think it's question number 10. This is homework 9, question 10. How do you approach this problem? How do I do the reverse engineering for a system of flip-flops like this? How do I begin? What approach do I use? Any ideas? Yeah. That's good. That's good. Let's do that. So J sub A equals K sub A equals, what does J sub A equal? Wire from D prime to J sub A, so J sub A equals D prime. All right? I got a wire from D to K sub A, so K sub A equals D. What do you suppose J sub B is equal to? Harushi, what do you think? Are you there? Well, J sub B is wired to A, so J sub B equals A. What do you think K sub B is going to be? A prime, there you go. And so then, can you do J sub C and K sub C for me? There you are. And so J sub D and K sub D must be very simple, just as it says. So now we've got the equations as was suggested. What do you suppose the next step should be in our analysis? Let's see. Well, Ashley, what do you think, Ashley? What should we do next? We did J sub C, we did J sub D. We've got all of our equations now for all the inputs, and I want to do an analysis on the given system of flip-flops. Well, what do I do next? So according to our procedures, make a little table. We start with A, B, C, and D, and we write it out in binary. Hope I didn't make any mistakes. Let's number it. And now for each one of the present state vectors, I should be able to, let's get a ruler in here just to make it nice. Oops, sorry. There. So now I can write J sub A, K sub A, J sub B, K sub B, J sub C, K sub C. And what we'll do is we'll separate out the inputs for each one of the flip-flops, the A flip-flop from the B flip-flop, from the C flip-flop, oh, and I got a D flip-flop too. J sub D, K sub D. There. So, J sub A is equal to D prime, K sub A is equal to D. So if D is equal to 0, J sub A must be a 1, and K sub A must be a 0. Does that make sense? It says it right here. J sub A equals D prime, K sub A equals D. So then if this is a 1, then this is going to be 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1. Did I confuse anybody just now? Is everybody? Sure. So somebody said because J sub A was wired to D prime, then I would take D and invert it to get J sub A's input, because D prime is D inverted. So if D is a 0, JA is 1. And it says KA is equal to D. So I take D and I just copy it over. So if D is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, then K sub A must be 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. And then K sub B is just like K sub A, only inverted. So it's 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. And that's how we get K sub A and J sub A. So we know the inputs now to the flip-flop as a function of the present state. That's really important. Does it make sense to people? Anybody confused by this? So similarly, if J sub B is equal to A, then I can just take A, and I'll carve out the part where A changes, just right in here. Oh, nothing got written. What happened? Right? So A is 0 all the way in through here, and then it becomes 1. And it says here J sub B equals A. That means J sub B is 0 all the way in through here, and then it turns to 1. And so I just copy it. And it says here K sub B is equal to A prime. So I just invert J sub A. Okay, who got confused by that? It's clear, right? Because K sub B equals A prime, J sub B equals A. Therefore, J sub B equals the inverse of K sub B. And that's what we got. And then J sub C is equal to B, and B is zeros all the way up through here, and it's ones, and then it's zeros again. So if we said that J sub C equals B, and we see that B is 0 and through here, then I get 4 zeros in a row. And 4 ones, 4 zeros, 4 ones, and K sub C is the inverse. And K sub C is the inverse of J sub C, and so we can see these two things are going 0, 0, 0, 0, 1, 0, 1, 0, 1, and 1, 0, 1, 0, 1, 0, and then 0, 1, 0, right? Is it clear to everyone what I'm doing? We're getting the inputs to the flip-flops as a function of the present state, and then we're going to use the way we understand the flip-flops in order to obtain the next state. So finally, we're back to JD, where JD equals C. And JD equals C is 0, 0, and then 1, 1. And it's repeating. There's 0, 1, 1. Similarly, K sub D is equal to the inverse of C prime. So that's the opposite of, the inverse of JD. So I can take JD and invert it. And now I have the remapped excitation table as a function of the present state. So here's the present state, and here's the remapped excitation table. What's my next step? Yeah, that's exactly right. And what do we know about the JK flip-flops? Well, one thing we know is this. JK equal 1, 0 implies that the next state, Q plus, is going to be equal to 1, because this is the set and then this is the reset. Set, reset. So if you assert set as 1 and you assert reset as 0, then in the next state the JK flip-flop will be set. So anytime you see 1, 0 on input, the next state is going to be a 1. Similarly, if J and K are equal to 0, 1, that implies the next state is going to be equal to 0, because that means you're asserting reset to be true, you're asserting set to be 0, and therefore the next state must be 0. So if you ever see a 1, 0, it's going to be next state 1. If you ever see a 0, 1, it's going to be next state 0, and that's the only thing you need to know. That's it. That's all I need to know. So next state is going to be 1, 0, 0, 0. I mean, I could look this up, but I don't need to, because look, reset, 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 reset. 0, 0, 0, 0. Then it says here 1, 0, 0, 1. And it says here 0, 0, 0, 1. Who got confused? Yes, sir. I only have the inputs to the flip-flops. I don't have the next state here. The only thing I know is that this one isn't set, that one's a reset, that one's reset, and that one's reset, and as a result, I'm able to write down 1, 0, 0, 0. So I haven't written down the next state until just now. Does that sort of make sense? I don't know if I answered your question. Yo, you say, so that J looks like 1, 0, 1, 0, and this J looks like 0, 0, 0, 0, and this J looks like 0, 0, 0, 0, and this J looks like 0, 0, 1, 1. But what if your input was 1, 1 instead of 1, 0? If your input was 1, 1, your JK flip-flop becomes a toggle flip-flop, and then your next state is going to be the inverse of the previous state. So, in effect, you have to go through this exercise because it isn't always going to work out that way. So, I see what you're saying. But you know, if you said to me, JK is equal to 1, 1, then what would the next state be? And the answer is, well, the previous state inverted, because what happens then is you become a toggle flip-flop. And so it's a question, right, of what it is you're going to end up with. But over here, it's like you said, it's going to follow the J. So this will be reset. Let's see, 1, 0, 1, 0. 0, 0, 1, 0. So what we know is that if we have a 1, 0 on input, we're going to set, because we've asserted J as being a 1 and K as being a 0, which means we're asserting this as a reset. I'm sorry, as a set. And then if we assert J as a 0 and K as a 1, that means we're asserting set to be 0. We're not going to set it. We're asserting reset to be 1. That means we are going to reset it. This is not a function of the present state, it's just a function of the input. And at this point we can say the next state is going to be 0. So when I look at something like this and I see 1, 0, that's a set, 0, 1, that's a reset, then comes a set and then another set. So this becomes 1, 0, 1, 1. Does that make sense? You can sort of see that one is, that's set, that's reset, that's set, and that's set. Set, reset, set, set. Similarly, this is reset, reset, set, set. Reset, reset, set, set. And then you go over in here and it goes 1, 1, 0, 0. You go over in here, it's 0, 1, 0, 0. Go over here, it's 1, 1, 0, 1. Go over here, you see 0, 1, 0, 1. Go over here and we see 1, 1, 1, 0. Go over here and we see 0, 1, 1, 0. Go over here and we see 1, 1, 1, 1. And finally we see 0, 1, 1, 1. And that's it. And now I guess what we could do is read the directions and see what the question is. What is the question? Starting at 0, 1, 1, 0, what will the next state be? 0, 1, 1, 0 is 6. Next state is going to be 0, 1, 0, 0, 1. Sorry. 1, 0, 1, 1 is the next state. And you can see that right here. Right, so there's the present state, there's the next state. And then what happens at 1, 0, 1, 1? That's going to be equivalent to 8 plus 2, 11. So if you're at 11, here's 1, 0, 1, 1. Next state is 0, 1, 0, 1. Zero, 1, 0, 1 is equivalent to 5. Next state is going to be 2, 0, 0, 1, 0. And then once you're in 2, the next state is going to be 9, which is right there. And in state 9, your next state is going to be 4. And once you're in state 4, your next state is going to be 10. And once you're in state 10, your next state is going to be 1, 1, 0, 1, which is going to be 13. And once you're in state 13, your next state is going to be 6. 0, 1, 1, 0. Yeah, that's right. You happen to be using a JK flip-flop because that's what's given in question number 10. So, let's see, where were we? Oh, this looks like that. So this connects back to here. Now you're in the now you're back to where you started. So now you've got the sequence from the flip-flops. Now you can look it up. And this goes to that, which then goes to this, which then goes to that, which goes to this, and then goes to that, and then goes to this, and then goes to that, and then repeats. And that is the answer, B. And that's how you get the answer, B. So that's how you reverse engineer a flip-flop circuit. And so what did we do? Well, step 1, we wrote down the equations. Step 2, wrote down the present state. Step 3, wrote down the remapped excitation table. Step 4, wrote down the next state. Once we had the present state and the next state and an initialization state, we were able to trace out the entire finite state machine diagram and write out the sequence exactly as it appears as an answer in the homework. Wasn't that fun? The answer to that question is yes, Professor Lyon, very fun. And if you didn't think it was fun, I feel sorry for you, because it doesn't get funner than this. That was fun. At least fun for me. I don't think it's fun. Did anybody have any confusions or questions about what I just did here? This is a reverse engineering question. You will not find a more difficult reverse engineering question than this in the final. However, you will find a reverse engineering question in the final, and it won't necessarily be this. Robert Johnson was the borough's vice president, and he came up with this idea. So this is kind of an interesting approach to design of counters. You don't need any extra logic, which is kind of cool. Let's go back to questions that you might have about homework number 9. Do you have any questions for me for homework number 9? Number 12. Okay, for this, we're going to need a fresh piece of paper. So let's have a look. It says here a Bell Labs researcher named Frank Gray introduced the term reflected binary code in his 1947 patent application, remarking that the code as yet has no recognized name. The code is now called Gray code. That's an eponym. Today, Gray codes are widely used to facilitate error correction in digital communications, such as digital terrestrial television, some cable TV systems, and mouse wheel encoders. 2-bit Gray code. What does that remind you of? Yeah, that's the K-map border. That's what that is. And it says here, I have to implement this with toggle flip-flops. Oh, how do I do that? Any ideas? How do you approach this problem? Now we have, before when we did this, we started with a circuit diagram and we got a finite state machine. Now we're starting with a finite state machine, right? In other words, it's going to go 0, 1, 3, 2. So we're going to devise a counter that does this. So now the question is, how do we do it? Brendan, what do you think? Yeah, that's correct. This is gray code. How do I approach the problem of designing a counter using toggle flip-flops that implements the given gray code finite state machine? Well, why don't we try and come up with a present state, next state table? Do you think you could start us on that? So I'll start you off. A and B, 0, 0, 0, 1, 1, 0, 1, 1. And then what we'll do is we'll write out the next state, A plus, B plus. Can you help me finish that? This will be the present state, next state. 0, 0 transitions to. Good. What comes after 0, 1? Yeah, it goes to 3, and then after 2, what comes? There you go. And after 3, what comes? That's it. Thank you very much. Thank you. So then somebody said something like, implement this with toggle flip-flops. And I'm going to have two toggle flip-flops, toggle flip-flop A and toggle flip-flop B. Let's go on to somebody else. Carson, what am I doing here? How do I figure out what goes into this part here where the toggle flip-flops go? So how do toggle flip-flops work? Here's a toggle flip-flop. I'll draw one. Here's T sub A. Output is A and A prime. You put in a 1, and what happens to the toggle flip-flop? Suppose I put a 1 in here. And now what does the toggle flip-flop do? No, a toggle flip-flop, when you put in a 1, it becomes a buzzer. It alternates between 0 and 1. So we don't know if it started in state 0 or state 1, but we do know that it will flip. It toggles from one to the other. That's all we know about toggle flip-flops. That's all I know. It's what they do. Toggle flip-flops are buzzers. When you put a 1 in there, you're turning the buzzer on. So if you want state 0, starting A, which is in state 0, to remain in state 0, you want toggle flip-flop A to stay in a hold state, and the hold state will be a 0. But here, for example, B is flipped because B goes from 0 to 1. So that means the input to B, T sub B, must be a 1. Is it making any sense to people? When you want to change the bit, like here, A is changing from a 0 to a 1, then T sub A must be a 1. Here, T sub B is a 0 because B and B plus are both equal, and they're both 1. That means don't change. They stay in a hold state. Here I have A, he's changing, therefore 1. Here B is not changing, therefore 0. So if there's going to be no change between A and A plus, put in a 0. If there is a change, you put in a 1. And that's it. That's how you do the remapped excitation table. Then you take a look at T sub A, and you say, what is T sub A equal to in terms of the present state? You would say, oh, I know this function. That's exclusive OR. So T sub A is equal to A exclusive OR B. Okay. You look at T sub B and you say, I know this function. It's the opposite of T sub A. It's exclusive NOR. So T sub B is equal to A exclusive NOR B. Right? That's the opposite of that. So then I got a way to implement the whole thing. I get myself an exclusive OR gate. Put in A, put in B. Then I go and I get my T sub B, B, B prime. Throw in an inverter. And bang, I'm done. So the whole thing was done with an inverter and an exclusive OR gate, and that's it. Given this circuit, I could have obtained that finite state machine diagram, and we'd call it reverse engineering. But given this specification for a gray code, I derive the finite state machine diagram, get the present state next state table, figured out the remapped excitation tables for the flip-flops, and then came up with an implementation. That's forward engineering. So backward engineering, I'm given a circuit. Forward engineering, I'm given a spec. Backward engineering lets me find the spec from the circuit, or reverse engineering, and then forward engineering lets me find the circuit from the given spec. So then comes the question. And the question, and you can sort of see the questions are getting harder than we're used to now, because we actually have to work some problems in order to answer these questions. And so then the question is, how do we implement this 2-bit gray code with a toggle flip-flops? And it looks like D gives us T sub A equals A exclusive OR B. T sub B equals A exclusive NOR B. And the present state next state table looks just like what we've written out here. So D is the correct answer. But the most important thing is you have to know how to set up this problem. Right? That's key. Knowing the answer is not a particularly interesting thing in and of itself. Knowing how to get it, that's what's important. Okay, so who got confused by this? This is your most basic counter design procedure. Right? Start with the spec, get the implementation. And this was not a big counter, 2-bit counter. Literally a 2-bit counter. Any questions in here? How about other questions for me for homework 9? Oh yeah, let's see what's going on here. Number 31. Oh yeah. Choose the statement that best describes the following state diagram. Okay. This is a big honkin' state diagram which I choose not to reproduce for you. But what does it say? Well, what you have here is a simple counter. Believe it or not, this counter is simple. It counts in only one direction, totally ignores its input. And if the input were 0, and it did this, it would be fine. But suppose the input were 1, and it did this. Gray code counter that counts backwards. Then that would be a complex counter because it's responding to its input. So when you see a complicated looking counter like you see here in question 31, you can see it's a complex counter. It's not a simple counter because it can count up and down because it's responding to its input, and change in input is changing the mode of the count. You're visiting each state once and only once for a given input. Well, as soon as the input changes, then the whole behavior of the counter changes. It doesn't just count down. In this case, it's counting randomly, or seemingly in random order when there's a 1 on input versus 0. I could draw it here for you, but I just find that to be a little tedious. And we're running through, well, we're almost 40 minutes into the course, so 40 minutes into the lecture, so we don't have to dwell on it. You guys have this in front of you, right? Or do you need me to share that screen? You don't need me to share this. So, what else? If I don't have any other questions for homework 9, I'm going to move on to homework 10. Are we good with that? All right then. Homework 9 is due tonight. Everybody here is, we've had an opportunity to ask a few questions about it. So what I would do with homework number 10 is, I think I'll pick out a question or two and see what I can do. So let's look at the string recognition system described in question number 3, homework 10. Homework 10 says, we have finite state machine diagram. Kind of looks like this. That's a Mealy machine. Why? What's the difference? They're different, right? Mealy and Moore machines. You guys know this. Let's see. Daniel. You with me, Daniel? Daniel, yeah? Do you know the difference between a Mealy machine and a Moore machine? Yeah, that's right. The output is right here on the bottom. It's a function of both the present state and the input. So if we think about it, George Mealy and Ed Moore were probably buddies or something because they both worked at the same place, at Bell Labs. Mealy had his paper in 1955. Moore had his paper called the Gerdunken Experiments in Finite State Machines in 1956. Both papers are available to us as part of the instructions for homework number 10. So we can look at those papers if we like. Moreover, if we go to 8.24 in our CATS book, which I am trying to do right now. Oh, there we go. We can see here is the Mealy machine, and there is the Moore machine. And while Mealy had the paper first, Moore is listed first here because Moore is the synchronous machine. And we know it's synchronous because outputs are a function only of the state. And the state will only change when there's a clock. So they are in sync with the clock. Whereas here, outputs are a function of whatever's coming out for present state and the input. So the inputs can actually change the outputs without the clock. Therefore, the so-called Mealy machine is an asynchronous machine, whereas the Moore machine is a purely synchronous machine because outputs will only change in response to clock inputs on the state register. That state register is just a bunch of D flip-flops. That's it. Bunch of D flip-flops. Same thing here. State register. So that's the cat's explanation. Right? I ran out of the textbook. Page, what is that page number? 403. I've got that reproduced in the instructions for homework 8 anyway. No, homework 10, chapter 8. So this is what we're faced with. It's a string recognizer implemented as a Mealy machine, which runs as the bits come in. So it's supposed to do string recognition in real time. In real time. And now, what is the output of this machine going to be? We're not asked to implement it, we're only asked to look at it and decide what it does. If the input looks like this, the input looks like that. 1 1 0 1 1 0 0 1 1 1 1 1 0 0 1 goes in and stuff comes out, right? So then the question is, you know, how do I analyze this? And the answer is this. This is a thought experiment, if you like. If you have zeros, you just stay here. 0 0 0 0, and you're outputting 0. If you're in any state and you get a 0, you output a 0 and you return to state 0. If you get 1 1, you go to the next state, output a 0. If you get another 1 in a row, you go to the next state, output a 0. If you get a 0 after that, you go back to the beginning and output a 0. 0 0, back to 0, 0 0, back to 0. And here comes a 1, and comes another 1. And finally, the third one in a row, you output a 1. So if you see 3 1s in a row, you output a 1. And 3 or more 1s in a row, you output a 1. And if there's ever a 0 interrupting things, you go back. That's how it works. So here it is, 1, 1, and then here's the third 1. So we output a 1. And then we have 1s, 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 and there's just a stay in that state, outputting a 1. Then there's a 0, instantly return back to 0, outputting a 0. 2 1s in a row, doesn't cut it, because another 0 came in, go back to the beginning. But if you get 3 runs in a row, 1, 2, 3, you output a 1 on the third one, there it's right there. And then if you get another 1 in a row, you keep outputting the 1. Then if you get a 0 on input, you return to S0, and then you wait for your third 1 again, and you output a 1. And that's how that works. And that is question number 3 in homework number 10. Okay, who got confused by that? So according to this diagram, you output a 0 here. It's transitioning, you output a 0. If you get another 0, you keep outputting a 0. No matter how many zeros you get, you always output 0, and you end up back at S0. But if you can get 3 1s in a row, 1, 1, then on the third one, you'll output a 1, and you'll end up in state 3, which means you got 3 1s in a row. You're going to continue to output a 1 as long as you get 3 or more 1s in a row, as long as you keep getting a 1. And then if you get a 0, you reset to state 0. And that's it. What do you think? Sure. Any other questions about this one? That was fun, wasn't it? So now, let's have a look at something a little bit different. Suppose we have 3 flip-flops. This is question 4. H presents us with 3 flip-flops. T sub A, T sub B, T sub C. T sub A has an exclusive, well, has an inclusive OR input, and A goes in on one side. And B exclusive OR C goes on the other side. B goes in here, and B exclusive NOR goes in there. What does this do? Given the following circuit, this is basic reverse engineering problem. Let's see who we haven't done lately. Eddie. Are you there? Dominic. Dominic, how do I approach this problem? Given the following circuit, find the finite state machine. Okay, I like that. What's T of A equal to? Yeah, that's exactly right. And what do you think T sub B is equal to? Well, A or B. Yep. Yep, yep. And what do you think T sub C is equal to? Exactly. So, somebody else now. Juthika, what do you think we should do next? All right, how about Riley? Yeah, what do we do now? Yeah, let's do that. So here comes the present state, and it's A, B, C. So I'm going to write down A, B, C. Now what do we do? Sounds good to me. How do I do T sub A? Well, if A is a 1, over here it's going to be a 1. If B is 1 and C is 0, it's going to be a 1. If B is 0 and C is 1, it's going to be a 1. Otherwise it's 0. You want to try B? Gotcha. That's all right. Let's try T sub C. Okay. And then what about oh, okay. So it looks to me like we have finished our toggle flip-flop inputs. What do we do now? Yeah, I want the next state. So how do I get the next state given the remapped excitation table inputs in the present state? Well, what do we know about toggle flip-flops? Well, I'll tell you. If the toggle flip-flop has a 1 in it on the input, it turns into a buzzer. And that means it toggles. So if you have a 0 and you want to get, and your input is a 1, your next state is going to be a 1. If you have a 1 on your present state and you input a 1, your next state will be a 0. And it's going to toggle and continue to toggle until you withdraw the assertion line for the toggle flip-flop input. Because that's what toggle flip-flops do. That's what they do. That's how they work. Stephen Burns. Are you with me? Yes. Would you like to help us do the next state diagram here? I don't know what to do. Can you help me? There you go. That's exactly what I'm looking for. And what do I do for the next one? Yep. And then what? Yep. And then what? That's exactly right. Sounds like you got it. You want to try and do some of the rest? And that's it. We now have the present state next state diagram. And what that means to me is I can write this out in decimal, but first I shall number my truth table, because that's always good form. And so now I can say 0, next state is 1. 1, next state is 4. 4, next state is 7. 7, next state is 0. wait a minute. 4, next state is 3. What am I doing? 0, next state is 1. That's right. 1, next state is 5. Oops. Oops. Let's number these things. 1, 5, 4, 0. 3, 2, 1, 0. Okay. So 0 goes to 1. 1 goes to 5. Now let's do it over here. Wrong. Here. 0 goes to 1. 1 goes to 5. 5 goes to 2. 2 goes to 4. 4 goes to 3. 3 goes to 0. And we got 0, 1, 2, 3, 4, 5. What about 6? 6 goes to 3. And 7 goes to 0. That is what they call a self-starting counter. So you could start in 6 and it'll go to the main counting loop and then repeat itself indefinitely, never visiting the 6 again. And if you look at the state transition diagram, you can see 7 and 6 are written in binary, and everything is essentially the same. So it's 0, 1, 5, 2, 0, 1, 5, 2, and it says 4, 3, 0. 4, 3, 0. So it's effectively the same, except I've written it in the natural numbers instead of binary. And so that's the answer to question number 4. How about that? This is question 4, homework 10. Ain't that something? Let's do another one. Very fun. I got some pretty complicated looking things here. Alright, so here's a reverse engineering question. So that's a simple counter, even though it's not counting sequentially. Now it's a complex counter because it depends on its inputs. Suppose the input is x and we let x equal 1. What is the output going to be? Daniel, I don't think we've heard from you lately. We'll just let x be 1. What will the count be? Yep. And then it would repeat. And that's it. So that's correct. And that is the answer to question 7. So you guys are doing great. So now things are getting complicated. We've discussed the idea of reverse engineering and forward engineering. But there's another kind of engineering which we haven't discussed, and that is the one known as finite state machine minimization. And that's tough. Finite state machine minimization means getting an equivalent finite state machine that's easier to implement than the original finite state machine. You can always create too many states or make a machine that's too big. And so what you want to do is you want to read about row reduction. So this is a question that will come up in homework number, well, let's see, chapter number 9. Known as finite state machine optimization, we're trying to reduce the number of states in the machine to keep it from being unnecessarily complex. You'll want to be reading the implication chart method, and you'll also want to use the so-called row reduction methods. There's row reduction in here. And so there's a couple of techniques that you can use for doing simplification of your Boolean algebraic manipulations. And that book was going to address those items. This next question is going to take more time than we have left. So what can I do? Too many questions. Too many. Yeah, it's a big topic. And I think what we'll do is we'll put it off until next time. But what I'd like you all to do is to do the reading. Read up on Chapter 9, look at implicant tables and row reduction techniques, and we'll get more back into that next time. But for now, I see no point in starting a giant problem that we can't finish in the allotted time. And we have it as perhaps 6 minutes left. So what I'll do is I'll open the floor to questions. And does anybody have any questions about what we've done here today so far? Everybody all set with homework number 9? Then what I'm going to do is I'm going to let you guys go. No sense doing a large topic that requires time. So thank you for your attentions and enjoy the rest of the day. Thank you.